3.2 Images formed by a convex lens. 1. Images formed by a convex lens. A convex lens forms different types of image depending on the object distance. The object formed is real and inverted when the object distance is longer than its focal length, but becomes virtual and erect if the object distance is shorter than its focal length. Your teacher will let you do the experiment below in the next lesson. Let's now take a look of the video first.
Place a convex lens in front of an illuminated letter F. Place a translucent screen behind the lens. Adjust the position of the screen until a clear image is obtained. Since the image can be captured on a screen, it is a real image. If we move the screen slightly closer to or further away from the lens, what will happen to the image? Now, slowly remove the screen. Can you still see the image? Move the convex lens towards the ray box until their distance becomes 5 centimeters. Can you capture the image on a screen now?
A real image can be projected onto a screen. The light rays from a single point of the object pass through the lens are first converged to the single point, and so the light rays received by the eye appear to come from that point, which is a real image. With a screen, the light rays may form a clear image on the screen, and so a real image is projected on the screen. A real image on the screen allows observers from almost all directions to see the image. Without a screen, the observer must be within a certain angle where there is reflected light rays to see the image. A virtual image cannot be projected onto a screen. The light rays from a single point of the object pass through the lens are not converged to the single point, but appear to come from a point located by drawing virtual rays. If there is a screen, there will be no image projected on this screen. 2. Graphical constructions of images. While there are 100,000 light rays emitted from an object, we draw only a few of them to locate the image. The construction rules help us to draw ray diagrams for lenses and hence locate the image and find its lecture.
Direct a light ray from a ray box. Slowly slide a convex lens perpendicularly across the light ray. Notice how the ray passes through the lens at different positions. When the light ray passes through the optical center of the lens, the ray travels straight without bending. Where is the optical center of the lens? Draw a straight line that passes through the optical center and perpendicular to the lens. This line represents the principal axis. Direct several light rays parallel to the principal axis onto the lens. Notice how the rays are refracted. The point where the light rays converge is the focus of the lens. Measure the focal length of the lens with a ruler. What is the focal length? Finally, direct a light ray to the lens along 3 different directions as shown. How does the light ray pass through the lens in each case?
So, there are 3 construction rules for convex lens. We may draw any 2 of them to locate the image for different object distance. The steps are illustrated here on your book. Note that all light rays from a single point of the object should pass through the same point of the image. In this way, you will be able to draw the refracted ray of any light ray emitted from the object. The light ray passes through the center of the lens goes straight. The light ray passes through the center of the lens goes straight. When a light ray not belongs to the construction rules passes through a lens, its refracted ray can be found by drawing a parallel light ray passes through the center of the lens. The 2 light rays should converge on the focal plane, and hence the unknown refracted ray is found. By the way, a convex lens always forms an image of a distant object on the focal plane. This is the simplest, quick method to estimate the focal length of a convex lens. Exam link 1. Path of a ray passing through a convex lens. Try checkpoint 2 below.